Thank you very much, Steve, for those kind words. Good morning, ladies and gentlemen. It's my great pleasure to come and speak to you today. I think before we get into isotopes or anything else, we'll talk a little bit about how isotopes work and how we use them to trace water cycle and water resources and how that information is useful. But probably the first question that you have in your mind that goes before the isotopes is, what are we doing here from the IAEA? And what does IAEA has to do with all this? Since you're all aware of the weapons and the inspectors and the safeties and the nuclear events and incidents and accidents. So those who, some of you may be aware, the International Atomic Energy Agency was conceived initially by President Eisenhower as a means to share the benefits of nuclear science and technology without everybody necessarily having to deal with or to involve themselves in the understanding and the use of the nuclear fuel cycle for weapons. And as a result, when it was finally established in 1957, it had three major areas of work or responsibility or the mandate: the nuclear safety, nuclear security, and the peaceful use of nuclear science and technology for nuclear power, for health, for environment, for food and agriculture and water resources. So whereas most of our work that is generally known is dealing with nuclear safety and security, the aspects related to the use of nuclear science and technology for development purposes is also a very important part of the mandate that we deal with. Within that mandate, then, you have the issues related to the development and operation and safe use of nuclear power, which is one major area of application for nuclear science. The second is the use of isotopes and radioactivity for health. So, all of you have some experience with or dealt with X-rays or MRIs or radiotherapies, and all of those are derivatives of nuclear science and technology, for which there are needs for normative standards and practices which IAEA gets involved with, or the safety of those sources that are used for those purposes. And similarly, then, you move into the area of water resources, where we don't use radioactivity that has been applied to the environment, but use radioactivity and its products that are naturally occurring. So that is where you have isotopes of elements like hydrogen and oxygen, and radioactive isotopes which normally exist in the environment, like carbon-14 or tritium and several other isotopes. So this is how the IAEA gets into the business of water resources and how the water resources work. So the aspects of water isotopes that I'm going to talk to you about today a little bit is the stable isotopes of oxygen and hydrogen, and also show you, and also, of course, the radioactive isotopes of tritium and carbon and some gases that are used to understand the age of water in the environment. So I'm sorry I had to use my computer because I wasn't organized enough to be here an hour earlier and set everything up. And now the remote mouse doesn't work, so I'm just going to have to use the expert assistance that has been kindly offered. So I want you to watch this video for a couple of minutes, and I'll give you a couple of comments while we are watching. This is essentially showing the water cycle, brought to you the courtesy of NASA, which shows the evaporation, condensation, precipitation. And once you have precipitation, all that water goes into the rivers, and then some of it into the ground, becomes the groundwater flow. And finally, that groundwater comes into the rivers, and some of it goes back into the sea under the water surface itself. So evaporation, precipitation, down into the rivers and lakes and ground, and back into the sea. So sea to atmosphere to river to sea is a water cycle, is the water cycle that is known to man for thousands of years. And most civilizations have attempted to have some understanding of what this water cycle does, how it works approximately, what time scales it works at, what influences it to some extent. There have been measurements of rain in order to manage some of the resources. You can hear that in the Nile civilization, in the Indus Valley civilization, in China, and in the Middle East, everywhere. You will find, if you look at the records or the historical descriptions or the scriptures of different religions, you will find some reference to water cycle. So it is not something new that we came upon today to learn that there is a water cycle that exists. Our issues that remain are that water cycle and its understanding are a key to sustainable management of resources, but our ability to fully understand it is very limited. So if you had looked at the weather forecast for Vienna on Friday, it would have said it was going to rain all week. But by Saturday, it was slightly different. On Sunday, it was different. It did become a little cooler. It did rain a little bit, but it did not rain as much as they predicted on Friday. And that is because not only do we have issues understanding the longer-term causes and effects on the water cycle, we have bigger issues in understanding the short term. And those occur generally because of seasons when you have transitional weather. So if you want to forecast in the middle of summer, probably will be more reliable than in spring when things are changing much, much faster. So the ability to understand the water cycle remains an issue, even though we know of its existence for a very long time. So when we talk about this water cycle and the water that it provides, we see rain, we see rivers, we see lakes, and we use them and we are subjected to their fury and everything else. But that water that exists in these reservoirs of rain and rivers and lakes is still a very small fraction of all the water that exists on Earth. Most of the water that exists is in the sea, which is 97.5%. It's salty, cannot be used directly for consumption by humans or human uses. You have to desalinate before you can use it. And of all the 2.5% or so that is left, a lot of it is locked up in the ice. So global warming might produce some more water, but only at a rapid pace in a few short months, and create more problems than solve the availability of water. Then 1/3 of all the fresh water that is left outside of the ice, 2/3 of that actually exists as groundwater. And we use the groundwater very commonly and all the time through wells, through springs that feed the rivers or feed the taps or whatever else. But we rarely appreciate the importance and the lack of understanding that exists for groundwater. And this is a resource that is beneath our feet, difficult to see. It's out of sight and out of mind except when we use it. And then we don't appreciate how difficult it is to get it, to use it, and how precious it is because it has existed and will exist whether it rains or doesn't rain, until we make it unusable or we empty it out. It's not going to be refilled that quickly. So that is why it is important for us to, excuse me, to not only understand, not only know how the river and the rain, how the rain and the rivers work, but also to understand better how the groundwater works. And that is where a lot of the effort is expended today if you want to alleviate or mitigate the immediate effects of drought, of lack of availability in the rural areas of water, lack of availability of water in rural areas. You see, if you go to YouTube or somewhere and type in, Africa and groundwater wells, or anywhere, groundwater and or water somewhere, most of the hits you will see will be people assisting local populations with digging a well, or putting a pump on a well, or improving the availability of water coming out of a well. But where does that well go? And where do you find that water, and how do you find it easily, is a problem. It's a huge problem. Even if you want to have some money to drill wells, many times half or more than half of that money is not necessarily usable, because we end up with either a poor quality water or a bad quality, or a lack of water, even when you drill boreholes. So you have to understand and map the resources. You have to know where they are. Generally, there is a struggle between trying to find where it is versus trying to map it. And mapping always lags much farther behind the need to use it now and today. That is where the human problem is. So our efforts are focused on trying to map the resources as much as possible and as easily and rapidly as possible, without spending relatively or as small amount of money as possible. And that is where the isotopes have their most immediate and most relevant benefit in the hydrogeological side, so that because water and isotopes in water essentially contain the history of where the water originated and where it came from and where it is going and how fast it is moving. And that, in essence, is why isotopes are used to understand water resources and what is the use of that information for water resources and water sustainability. So if you go to the next one, not only is the water relatively less, the fresh water is relatively less in the form that is usable for humans, it also exists in a very uneven fashion over Earth. In general, where there is more population, there is less water. And there is more water, there is less population. And water is not transportable easily from one region of the Earth to the other region of the Earth. And that is where the water scarcity and water crises start, because there is a lot of water on Earth, even though we have only 30% of the fresh water available as fresh water. But in total, the water is quite a bit, but it is not enough where we need it. It is not enough when we need it. You can go to the monsoon regions, the tropical areas of the world, and there will be a lot of water that comes down in 2 or 3 months, and then you got to store it if you want to use the rest of the year, because it is not easily available unless you go to the ground, and then groundwater also has its limitations. So the crisis comes from the uneven distribution in space and time over Earth in terms of where and when the water is available. And if you not only go to YouTube and look for efforts, if you go to read the newspapers, and these are just some clippings from New York Times over the last couple of years, and well, they may be a little bit more dated than that now. I haven't updated them, but I think they are still the same. You will find them in different parts of the world. Same problems, urban or rural. Developing countries or developed countries have very similar issues of water in terms of availability and distribution. And here are some examples from China or from India. If you go to next, you will find some from the US, where the water levels in lakes and rivers and availability through rain in the south and southwest has been affecting the population substantially. And as I said to you before, this water cycle has impacted the humans for a long time. So once you have all of this, go back a little bit, and you didn't come up with another one. All right. Well, no, keep going forward. I was going to show that somehow when I transferred the slides from one to the next, it didn't show up. But the human response to this problem is very similar. And if you go back to the Egyptian civilization, the Nile civilization, you will find the god of water, the Sobek. And people prayed to God at that time to say that, bring us rain or do whatever else. And most civilizations is the same thing. But as technology has advanced, our response necessarily has not advanced, has not changed that differently. So the clip I was going to show was a clip from New York Times from 2007 that says, Georgia governor organizes a prayer for rain. So our response for understanding and lack of thereof of the water is the same as it was 5,000 years ago or it is today. Simply because our ability to understand and hopefully manipulate, but we can't really manipulate it that much, but the lack of ability to manipulate and to understand is what causes us to look for responses through events or the supernatural, as we all, one way or the other, have some understanding of that. So if we look at the stress on water resources, besides the distribution of the uneven distribution of water on Earth, where water does exist, of course it exists in almost all parts of the world that people are living in, but the overall demand for water has been increasing. And if you look at the data on that, it shows that from the 1950s onwards or 1900 onwards, you can see almost a linear or exponential increase, which has decreased to some extent over the last 30 years as people have become more aware of the stresses on water. And people have become more responsible in using the amount of water. And industrial use of water has decreased. Agricultural use of water has decreased to some extent. There have been conservation measures for domestic uses as well, which have somewhat slowed the growth of demand, but not necessarily at a level where it has become sustainable overall. Can you go back one, please, again? And there are basically three major demands. The population demand, which definitely we know will continue to grow. The agricultural and industrial demand is somewhat certain because it will grow at a certain rate, but not necessarily at the same rate as it was growing in the past. And the third one that we have is the climate change, for which the effects remain somewhat unpredictable at the moment. And one of those things you can see that, as groundwater is one of our major resources of fresh water and is usable in different parts of the world without necessarily too much effort and too much resources, is one also that is an insurance to some extent against climate change. So that, climate may change today, there may be no precipitation here today, but you can still have a well. You go to the deserts, you go to Sahara Desert, you still find oases, and you still find wells that can be dug and water can be found. That is water that is there from a very long time ago when the climate was different in that area. So even if the climate changes today in a certain area, you still have water resources available in that area, and that is the groundwater. But our ability to understand how much we have and how much it will change is relatively poor and relatively limited. And these are some predictions or models, different models, looking at the predicted change in groundwater recharge. But they are based upon projections from today and projections using current understanding, which is not necessarily the most reliable and appreciated, useful. And because of this lack of understanding and information, there have been continued recognition of the fact that we need information. We need more data. We need to understand where the resources are, how they're impacted, how they're renewed, how they're not renewed, how much is being used. And at least since the mid-70s, when more international events were taking place since then, highlighting the political and social issues related to water, there has been a constant recognition of the fact that we need more information. However, over the last 40 years, the need and the recognition for the information has increased quite a bit, but the gaps continue to be substantial. And that is where our effort is focused in trying to improve the availability of this information. And we have to use all of the tools that we have available to us. So over the last 20 years or so, the information from satellites has become available and is being used. And that has increased our understanding of how much water exists in which parts of the world and how much of it is being depleted or used and how quickly. That has improved our understanding a lot. It is still not at a scale that is small enough for us to use it completely quantitatively, but at a gross level, we have improved our understanding of the water resources through satellite information. When you come down to a local level, things like isotopes are extremely useful to understand the larger history by using a relatively small effort. So this isotope understanding or using isotopes for water resources or for understanding water cycle itself is an idea that kind of developed as soon as isotopes were kind of discovered. So oxygen was discovered in the late 20s, and hydrogen isotope deuterium was discovered in 1931 by Harold Urey. He was working at Columbia University at the time. And at the same time, the hydrological sciences also were evolving, and it was becoming clear that in order to understand any of these resources, the rivers and groundwater, we have to use some amount of time scale and larger scale understanding. And therefore, as soon as the isotopes were discovered, people tried to measure them in seawater and in rainwater, some two very easily available water resources or bodies of water. And immediately it was discovered that there were substantial differences in the ratios of oxygen and hydrogen in seawater versus fresh water, and therefore that gives an understanding that the only reason it can happen that way is by these changes occurring during evaporation. And if that is the case, we should be able to use isotopes to understand where the rains come from and what happens to the water cycle. So this idea of using stable isotopes to understand water movement became very clear very early, very immediately after the discovery of isotopes. But then, of course, we had other events on the world stage that took over, and some of these ideas remained half-baked during the Second World War, from the late 30s to the mid-40s. And during that time, while some of these ideas remained on the back burner, but there were additional information that was gained. The natural radioactivity of tritium and carbon-14, which had been discovered in the 30s, also were then measured, and it was found that there are significant differences in the, or that it is possible to measure the radioactivity of carbon and tritium in water, and therefore you should be able to use that to understand the age of water. So together, by the end of the 40s, it was clear that there were tools of stable isotopes and radioactive isotopes that can be used to understand water and the water cycle on Earth. And that is what led to, from 15 onwards, continuing today, continued use and development of the methods of isotopes in hydrology. The second event that happened that helped the use of isotopes for hydrological purposes was some of the nuclear testing for weapons that occurred in the late 50s or mid-50s to early 60s. After the initial research on weapons, on atomic weapons in the 30s and 40s, in the 50s, the race was towards the hydrogen bomb. And in order to get the hydrogen bomb, the explosions, the testing had to be done in the atmosphere. And while the testing was done in the atmosphere, that testing introduced a lot of tritium and carbon-14 into the atmosphere. The amount of tritium and carbon-14 then came back to Earth. So the issue was, well, is it dangerous? Is it difficult for us to manage with this in terms of health risks? So there was a need to monitor the amount of tritium and carbon-14 in rain starting from the late 50s. And as a result, when the IAEA was also established at the time, one of our first tasks in the area of water was to monitor this radioactivity in rain around the world. And when we were going to monitor the rain, the people designing the experiment at the time, or the monitoring at the time, also were aware of the fact that stable isotopes can be used to understand water resources. So therefore, the monitoring included both stable and tritium and carbon-14. The levels of tritium and carbon-14 that were found in the rain were not at a level that will raise concern for human health, but they were an excellent hydrological experiment. So it's like taking a tracer and dumping it over the earth and say, let's see what happens. And that is what gave us a substantial amount of knowledge for understanding water using isotopes. So this is a map of the distribution of oxygen isotopes in global rain. And this has been monitored in many stations around the world, and we fairly well understand what kind of isotope will fall in, or what kind of isotope ratio will exist in rainfall when it occurs in different parts of the world at different times of the year. Because the oxygen isotopes or hydrogen isotopes are determined in rain as a result of temperature and the source and movement of water in the atmosphere and the nature of rain that occurs. So, winter rain versus summer rain are different because the process which condenses water is different. And what we see here on a gross scale is that you see the blue colors at the top or at the very bottom, which is that the ratios, which are devised in negative numbers because we are not measuring anything absolute. We simply say, my hand is 5 feet from this chair or 3 feet from this chair. It doesn't matter where the chair is. And we decide on an international standard that everybody knows where this chair is. So we fix the chair and everybody measures their hand from that chair. So somebody can be positive, somebody can be negative, somebody can be here, but they're all measuring relative to one spot. So that is why it is a deviation or a relative scale of isotope measurement, and that is why you have numbers which are negative. But there is no negative ratio that exists in the world. It's only relative to a certain ratio. And what it shows is that you have more negative ratios in the top and somewhat variable in the middle, and again negative in the bottom, and that is because as the temperature is colder, the ratios are lower, more negative compared to a fixed standard. And that is why the gross pattern that you see there is that of temperature, which somewhat determines the distribution. And then, of course, you have summer and winter distribution as the same rate, and you have geographical distribution based upon the temperature and the nature of rain that occurs. So we talked about the natural radioactivity, and this is how the natural radioactivity comes. The cosmic particles interact with nitrogen in the upper atmosphere, and that produces both a tritium atom or a carbon-14 atom. And a tritium then is oxidized and becomes a part of the water molecule. So you have H2O, you have H3O, or not H3O, but 3HO. So it's a tritium oxygen and deuterium oxygen and a normal hydrogen oxygen. So H1, 1H2O and 3H2O or 2H2O. So normal hydrogen, deuterium, which is hydrogen 2, and tritium. All three of these molecules occur in rain. Similarly, carbon-14 is then oxidized, becomes carbon dioxide. That carbon dioxide is then used by plants for photosynthesis. That creates organic matter, soil gas, carbon dioxide. All of that is dissolved in water as it percolates underground. And that water then therefore contains carbon dioxide, which then dissolves the rocks, because carbon dioxide makes the pH of the water go down, makes it more acidic. And as that water goes into the rocks are dissolved. As a result of that dissolution, the water then contains hardness. Hardness is a combination of metal ions like calcium and magnesium and a carbonate ion. So you have CaCO3 or MgCO3 or things like those in water, which is the hardness. That hardness contains carbonate ion. The carbonate ion contains a carbon atom. And that carbon atom is a result of the carbon in the atmosphere, because the carbon dioxide comes from the plants. And the plants are constantly producing new carbon. And therefore, their activity, compared again to a standard, is 100%. So as long as the water is in contact with the atmosphere, its carbon activity, carbon-14 activity, is near 100%. Maybe a little bit less because we dissolve some of the old carbon from the rocks. But as soon as the water goes into the aquifer and is not in contact with the atmosphere, its activity then declines, simply because carbon-14 decays. It breaks down from carbon-14 to normal carbon-12. So as a result, you can measure, you can take out the carbonate, the hardness from the water, you separate it, you make a gas out of it, and you measure the activity of carbon-14 in that hardness of the water. And that gives you an understanding of the age of water. It's a little bit complicated. You have to understand, you have to make sure that you are measuring the carbonate. The hardness is actually all coming from the atmospheric CO2, and you can make some corrections, you can make some changes, but that is where the water that you get from a well contains hardness. You take out the hardness, you separate it, you measure carbon activity, and you get some idea of the age of water, which can tell you something about a few hundred to 1,000-year-old water to up to about 40, 50,000 years of water. Because the half-life of carbon-14 is about 5,700 years. And you can measure the activities in general for any radioactive element up to about 5 half-lives. So if you go to about 30,000 years, you will have some availability of carbon, but because there was some more carbon in the past, so you can actually go up to about 40,000. Tritium, on the other hand, has a half-life of 12.3 years. So you can use tritium to understand what happens in the last 50 years or so. You can extend that a little bit more by measuring the daughter product of helium that comes from the breakdown of tritium. So tritium goes and breaks into a helium atom, and helium is a noble gas which you can take out of the water and measure it, and you measure the tritium together with it, and you get an age of water that can give you an age somewhere from a few years, like a couple of years old, to up to about 60, 70 years. And you can measure those ages by using these radioactive elements. And we have, of course, also, as I said earlier, measured tritium in the past, just as we measured the stable isotopes. So we know what the tritium in the rain looks like, or the carbon-14 in the rain looks like around the world. So we know what the rain today is coming up with, and what rain came out with in the 1950s or 60s. So we can take that as a starting point, and we know how much of it should decay to give me an age of water. If I take out the water in the river today, in the Danube, I should be able to know where that came out. And if I go into the wells near the Danube, I know how far it took, how long it took for the Danube water to come to the well. So we can figure that out. The other thing that happens in the atmosphere, besides the stable isotopes, which reflect a lot of processes of formation of rain, tritium, on the other hand, is introduced once and just moves around. It doesn't change with how you form the rain. Wherever it was, it just comes out as much as it comes out. So when we monitored tritium, we also learned a lot about what happens to water in the atmosphere. Because in the beginning, when the testing was done for nuclear weapons, they were not every day, or they were not for a long period of time. One test was done, and then nothing happened for several months, and then another was done, and nothing happened for several months. What people noticed was that one test was done, and tritium increased in the rain after the testing was done. After a month, it was gone again. There was no tritium left. So what happened to all that tritium that went up? Well, so what occurred was immediately that the water, the atmospheric moisture, stays in the atmosphere for less than a couple of weeks. All of this rain that you see, all the clouds, all the moisture in the atmosphere, it is all renewed in about 10 days. The average lifetime of a water molecule in the atmosphere is about 8 days. And that is how we learned about tritium and its use in understanding the residence time of water, both in the atmosphere as well as in the ground, in the rivers, in lakes, and wherever else. The second thing that you see in this graph is most of this color is in the north. There's very little in the south. That's because testing of tritium or weapons was mostly done in the northern hemisphere. And the moisture on Earth, while it has an average lifetime of about 8 days, also is very tribal. And the northern guys stay in the north, and the southern guys stay in the south. And a little bit of mixing occurs around the equator. And that is why you do not see a substantial homogenization of moisture in the north and the south. And that is extremely valuable information for us to understand how the weather works and how the moisture moves, and then it is used for understanding and improving climate models or weather models. So obviously they haven't improved as much because it didn't rain this week very much, which is good, but that is how the information comes on understanding where the water comes from and how it forms by stable isotopes and how it moves by using tritium and carbon-14 and how long it has been away from the atmosphere by measuring the decline in their activities. And these are the three pieces of information that essentially give us the knowledge about isotopes, about water resources. But that knowledge is not in isolation. So even if I go and measure something and I find an age or find the origin, I still need to know what is the geology, what is the hydrology, how the system works, in order to use that information to inform my development of a better understanding of the entire system. So what information we get from here, from isotopes, is telling us about the large-scale functioning of the system, that the water is coming from one location, it's going down, it is moving at a certain rate. So it is giving me information about the infiltration and movement, but in order to use that information, I still have to understand the geology and the hydrology, except I will have a better understanding with less time and effort because I know overall, at a gross scale, how the system works. And that is how you improve the ability to map the resources by using large-scale information to develop smaller-scale knowledge, smaller-scale systems knowledge. And like I said, there are many different isotopes that can tell you the ages from a couple of years to millions of years, as we saw for the krypton. All right. So I think I partly answered this in the previous discussion. You know, what do we do with it? It's okay, it's good knowledge, but who cares? But the care part is that it can be used to solve real-world problems of today. Well, I was going to show you a video, but I think I'll pass that. I'm getting a little bit behind. So I'll just tell you one application. Sorry?
You have plenty of time.
I got plenty of time? Yeah. Oh, all right. Well, no, it's okay. Don't worry about it. I'll have to think about it again what it was then. So I'll just, but I will cut down the discussion of this one too much. Essentially what it is talking about is the situation of arsenic poisoning in Bangladesh. I don't know how many people are aware of it, but the issue with water resources and clean drinking water is that groundwater is a resource which is usable without treatment of problems with pollution or anything else, because generally it cleans itself under normal circumstances. So people who depend upon surface water only, like rivers and lakes, in water scarce areas or in areas like the tropical monsoon areas where rain comes once and stays and then you use the rest of the year, generally have polluted water resources. So they have contamination from bacteria and human and animal waste and everything else, and leads to disease. In order to overcome those diseases, the practice has been in the last several decades to increase the availability of groundwater as much as possible. And in this part of the world, in Bangladesh and parts of India, and now it's further away in many other parts of the Southeast Asia as well, the effort starting in the 1970s was to install these wells, relatively shallow wells, because these are easy sandy horizons, 30 meters or 40 meters deep, and use them, for irrigation, so that you can have more than one crop per year. You can have more economic activity and improve the livelihoods. And B, to drink clean water from the wells, which did both of its jobs for the 20, 30 years afterwards. However, the only problem was, in the 90s it was discovered that this water, which is great for agriculture, and for clean drinking water is actually not very clean. It contains arsenic, which is poisonous, and led to a lot of disease and arsenicosis or disease related to the excess arsenic. And now the point becomes, how do you mitigate this problem? In order to mitigate the problem, the first thing you need to understand is, where did this arsenic come from? What is this? All right. So where did the arsenic come from? What are its why does it exist? Did it exist because we started using the water and we caused the arsenic to come into the water? Or has it been there geologically under natural conditions, and we simply are not aware of the fact that this existed there? But that has to be known. At what depth it occurs? Is there safe water available anywhere in the ground, or is it all arsenic? And if it is somewhere it is safe, would it remain safe in the next 20 years, or are we going to create bigger problem in the 20 years by using an apparently safe water, which also becomes contaminated afterwards? And therefore, all of these questions need to be answered, but are very difficult to answer, because in this region of the world, it is a deltaic region. It is a delta of the very big rivers, the Ganges, the Brahmaputra, and the other rivers. And the sediments are not like layers. You don't have one layer of this and one layer of this and another layer of this. So you can easily say this layer is bad, this layer is okay. You go make a well at 30 meters here, you are in a different layer than if you go and drill 30 meters over here. So you can't really correlate anything. So it's a very difficult task to correlate the spatial variability in geological as well as arsenic distribution. What we could do, however, is we could look at the water, we could look at its isotopes, we could look at its age, and say whether water here is the same as water here, regardless of approximate what depth or what layer it may be found in. And that should be substantially useful to understand that. So what we were able to establish fairly early on, that there was a very good correlation between the water, the concentration of arsenic in its dissolved phase, and the age of water. As the water got older, it had more arsenic, and when it was younger, it had less arsenic. So from about 0 to 30 years or so, there was not as much arsenic, and but once you go higher, the arsenic concentrations also increased. Next one, please. And in fact, the 10-year-old water generally had less arsenic than a 35-year-old water. Now, if you remember, the pumping and the well development and everything started in the 1970s. So this was done in 2000. So 25, 30 years later, a 35-year-old water has more arsenic, means we didn't really cause the problem. That's very helpful. It probably existed by itself. It's a natural cause. We simply exploited it. You might say, well, that was not the first time water was used in that part of the world through wells. Why did it become a problem now if it existed before? The difference lies in the way it is used. Before all of these boreholes were developed, because you had the availability of hand pumps or motorized pumps, most of the water that was used from the ground was used from open dug wells. In open wells, water comes to the well, stays there for a while. You go there once in a while, you take a bucket out, and you use the water. While the water is in the well, it is in contact with the atmospheric oxygen. And that oxidizes arsenic and makes a coating of arsenic around the well, but it is out of the water. So if you were to still use it, take it out a bucket or 2 buckets at a time, leave it open for a while, or put it in a filter of some kind, and use it the next day, you may still be all right. But if you take it out of the pump and use it, whatever was there is now here. It hasn't gone anywhere. So therefore, even though there was arsenic present naturally, it was not a large-scale problem. Not too many people were using it. They were not definitely using it from boreholes. They were using it from open holes. and therefore most of it disappeared. But that doesn't solve all the problems, because these wells still exist, and people have a tendency, when you have something clean available and seeing, you want to use it still. So one of the efforts that was being made in that part was, well, at least we could ask people to desist or to avoid the use of those which have been contaminated and find new water, so that we can supply, at least to a community, water that is available and is clean. So now that effort becomes a large effort. The reason, remember, the groundwater was used was because it was relatively cheap, relatively inexpensive to use groundwater. You can put a pump, you can take it out, use it. There's no treatment, there's no chlorination, there's no killing of the bacteria or whatever else, no filtering, no nothing involved. Now, in order to provide clean water, either you take this dirty water out from the ground, you filter it, you treat it, you make it clean, and then supply it in a pipe to the households. Or you can take it from the river, once again, from the contaminated parts of the surface water. You treat them again for bacteria and metals, and then supply it. But treatment costs a lot of water, a lot of money, maintenance, capital costs. So how do we use isotopes in that area? Is that even though we can see the differences in arsenic in different parts of the similar region, but there are differences in the geology. If rocks are occurring from different ages and they have different types of sediments, some types of sediments do not have arsenic at all. Doesn't matter how long they stay, how long the water stays there. And if you find those kind of rocks, then even though arsenic doesn't exist today, it is likely not to exist tomorrow. So if we can find those kind of situations, we should be able to help use isotopes to identify those. So while in this village, for example, there's a small village in northwestern part of Bangladesh, there's a river that goes around like this, and there is some arsenic over here, and there's no arsenic over here, but it's not clear whether this arsenic will remain low or not remain low. So therefore, the design initially is that, okay, we'll take this water from the river, we'll put some big wells here, we'll treat them, and we'll supply the water. But if this arsenic-free water can be shown that it is from a different system, we don't have to do all that. We simply can go and put wells over here and use that water. When you look at the isotopes, you find, in fact, they are very different. Over here, you have a different shape of these isotope distributions compared to over here, and therefore, when you go look into the ground, what you find is that there, in fact, is a reason for those differences. The reason is that these are different kinds of sediments compared to these ones, and they are not normally communicating, which is obvious from the fact that these wells have always been arsenic-free compared to these. So you can save all that money. You simply put your wells over here, and you put it into the pipe system and monitor it and supply arsenic-free water.